Welcome back to the workshop for one more example on comparisons of series. For this example, what we're interested in doing is adding the comparison of series to our list of tests that can help us determine the convergence or divergence of a given series. For each of these series, we want to determine all of the possible tests that we could apply. Of course, we could apply any of them, but they might not give us a result. So we want to choose which tests we might be able to apply to give us results. Now, this doesn't guarantee in each case that it will, and I'm not saying which is necessarily the best. That's up for any individual to choose for themselves as they approach a problem. All right, so for our first series, the sum from 1 to infinity of 1 over the square root of n plus 9, I think the most obvious test to use in this case would actually be the limit comparison. And we could take the limit comparison with the sum from 1 to infinity of 1 over square root n, because we're effectively looking at the same thing. As n gets really large, that plus 9 isn't going to do a whole lot. Of course, this is a p-series that diverges, so we could use that to show that this diverges as well. But we could also use the direct comparison test. And we could, let's see here, we could increase the denominator to give us a smaller fraction and have something that still diverges. So we could compare this with the sum from 1 to infinity of 1 over n. Notice increasing the denominator gives us a smaller fraction, a smaller term in each case, and that allows us to say that since this thing, which is smaller, since that diverges, this thing, which is larger, must also diverge. And then, let's see here, there was one other test. Yes, the integral test could also be used for this example. In order to justify the use of the integral test, you have to confirm that the function that you're using is positive and that it is decreasing over the appropriate interval as well. So positive and decreasing. And then, of course, you would have to take a improper integral as well. Okay, for the next example, in this case, we have a geometric series. So the test that is just the geometric series test. Is it a geometric series? Yes. Okay. We have qualifications for where it converges or diverges, and we just apply that to our ratio. All right. That is the only test that would work in this case. It's not a p-series. If I wanted to, I can't apply the limit comparison or direct comparison or the integral test because these do not have, or this does not have all positive terms. So we would have to apply something else if it were not the geometric series. So we will also see further tests for alternating series as well. All right, geometric series in this case is the only test. Here, there's one test that's probably the most obvious and it would be the easiest, I would think, and that's the nth term test. And that's because if we were to look at the fraction or this rational expression, the numerator is polynomial degree 1, and in the denominator, if we could apply that square root, we would be taking a second degree polynomial down to a first degree. So first degree over first degree gives us the ratio of leading coefficients. Now we don't have exactly that in this case, but we should be able to observe quickly that the limit as n goes to infinity of these terms is not 0. So the nth term test would be the best way to go. It would be an excessive amount of work to come up with, well, maybe not an excessive, but it would just be much more work than you need to do to use the limit comparison or the direct comparison. both of which you could use the sum of 2 for, and then I believe you could also use the integral test. But each of these would require a bit more work than just observing that the nth term is non-zero. All right, for our next example, we again have something that is a geometric series. Notice that this is the sum of 1 over e to the n. So we could simply say a geometric series and be done with it. I would not necessarily encourage you to try any other method, but if we want to consider all methods that would work, it's worth noting that the integral test would also work in this case. The function e to the negative x is positive, and it is decreasing, so we could use the integral test as well. All right. Let's see here. Okay. For our next example, we have 1 over n times n plus 1, and again we have a large number of tests that would actually work. The first one, which may not be the most obvious, but you could observe this as a telescoping series. If you were to use partial fractions, you could separate that into 2 fractions, and it would be 1 over n minus 1 over n plus 1. Yes. So that would give you a telescoping series. You could also use the integral test. You can also use the limit comparison. And you can also use the direct comparison. In both cases, using the sum of 1 over n squared would work and give you what you're looking for. And then for the last example, we can observe this as, maybe just observing it as 6 times the sum of 1 over n to the 6th makes it absolutely clear that this is a p-series. So you could use p-series, and I would encourage you to use that in this case, because the only other thing that would make sense to use is the integral test, which I'm not even sure makes complete sense when you have p-series available to you. Of course, you could also do direct comparison with, actually I don't know that I would encourage a direct comparison. Well, you could probably use a direct comparison with the sum of 1 over n to the 5th. Let's see, because you are increasing the denominator. Sorry, you're decreasing the denominator and you're decreasing the numerator, so you want to be careful there. You want to make sure that you're decreasing the denominator by a larger factor than you're decreasing the numerator, so that way you have something bigger that still converges. So this is not true for all n. It will eventually be true. Or you could consider the limit comparison with the sum of 1 over n to the 6th. But again, I think that observing it as a p-series gets you what you need right away. The other tests aren't necessary. The main thing to take away from this example is hopefully a way to identify a test that works from the minimal discussion that we had, but more importantly is to recognize that there are options. There are a lot of options for you when it comes to determining the convergence or divergence of a series. So if you are not sure which one will work, you are welcome to try any of them, because frequently there will be multiple tests that work. So have no fear, don't feel overwhelmed. It can be a little bit daunting at times. There's a lot of different tests, But when you're tasked with just determining the convergence or divergence of one individual series, you can begin by just going through the list of tests. Try the nth term test, because if it diverges, likely, or if it's non-zero, then it diverges, and that's quick and easy. Beyond that, you just need to see if it fits this particular case, or maybe this particular case, and those are pretty quick to remove, typically, unless they're written in a very contrived way, which is possible. But then you just move down the list, and you say, all right, let's try this, let's try that. That didn't work. Okay, move on to the next. And that's not a big deal. A little time consuming, but as you practice, you'll become a little bit more familiar with the tests and how they might fit within a particular series to help you determine convergence or divergence. All right, I hope you guys have a wonderful day, and I will see you back here in the workshop again soon.